So let's say we have a very straightforward, easy sequence like the sequence a sub n equal to 2n over n plus 1. And you might be asked to find the first few terms of the sequence. Right, so I was going to find the first few, let's say the first 5 terms. I should point out, if they haven't said where the sequence starts, we typically assume it starts at n equals 1, although it is also usually correct to start at n equals 0. So kind of either way, it really depends on what you're told. But if no one says anything, you should probably just start at n equals 1. So the first 5 terms, a sub 1, this is really like a function, right? This is kind of like f of n, where you say, okay, I'm going to plug in n equals 1. And I'm going to get 2 times 1 over 1 plus 1, which is just 1. And then I'm going to find the next term. So the next term, a sub 2, is 2 times 2 over 2 plus 1, which is 4/3. And the next term, a sub 3, I'm going to plug in 3 and get 2 times 3 over 3 plus 1, which is 6/4, which we could reduce to 3 halves. And I'm going to plug in 4. A sub 4 is going to be 2 times 4 over 4 plus 1, which is 8/5. And the fifth term is going to be 2 times 5 over 5 plus 1, which is 10/6, which reduces to 5/3. So the first 5 terms of my sequence are 1, 4/3, 3 halves, 8/5, 5/3. And it goes on and on and on and on and on. Let's also look at the much further out term. So we could say, this is a sub 1, this is a sub 2, this is a sub 3, this is a sub 4, this is a sub 5. And then we could go out to, say, the 1000th term. And actually, I'm going to do the 999th term before I do the 1000th term. Let's do both the 999th term and the 1000th term. So the 999th term is going to be 2 times 999 over 999 plus 1, which 2 times 999 is 1,998, and that's 1,000. And 1,998 divided by 1,000 is 1.998. And then for 1,000, we get 2 times 1,000, which is 2,000, over 1,000 plus 1, which is 1,001. And even though this is a little bit more challenging to calculate, I think we can pretty much see it's pretty close to 2, right? The numbers are getting very, very close to 2 as a gets larger and larger and larger. So the question we want to answer really is, what does this sequence converge to? Or in other words, what is the limit of the sequence? So when you're asked if a sequence converges or what it converges to, you're being asked to find the limit as n goes to infinity. Now, you might be aware of various ways of attacking this limit. The kind of standard way is to divide. So when you have a rational function like this, where you have just powers of n on the top and powers of n on the bottom, the standard kind of way of doing this is divide the top and bottom by n to the highest power that occurs in the denominator. So the highest power of n is just n to the first. So I'm going to divide everything by n to the first. So I'm going to write 2n over n over n over n plus 1 over n. And then these simplify. 2n over n is just 2. n over n is just 1. So this is the limit as n goes to infinity of 2 over 1 plus 1 over n. As n gets really, really large, 1 over n gets really, really small. It goes to 0. So this limit is equal to 2 over 1 plus 0, which is just 2. So the limit of this sequence is 2. Those terms get closer and closer and closer and closer and closer to 2 as n gets larger and larger and larger.
I have a question.
Sure.
So with the 1 over n, did you know that that was 0 just because like 1 over a given number, it's going to get smaller and closer to 0?
As n gets larger, yeah. So you actually bring up a good point, Jack, which is that when we're evaluating limits like this, we typically use the following two things all the time. We have that the limit as n goes to infinity of 1 over n is 0. Because if you have a fraction where the denominator gets larger, the overall value gets smaller and smaller. And that's actually true for n to any positive power. So really more generally, it's the limit as n goes to infinity of 1 over n to any power that's positive. That's also going to be 0 for the same reason, because the denominator is getting very, very large, so the fraction is getting very, very small.
Okay, thank you.
You're welcome. Yeah, of course. So this is kind of the idea. We could also look at another sequence, like a sub n equal to, I don't know, 3n squared over n squared plus 1. And while we could write out the first few terms, right, it gets a little bit old, right? So the first 5 terms, it is good to be able to do this relatively rapidly. So like if I plug in 1, I'm going to get 3 over 1 plus 1. That's a1. If I plug in 2, 3 times 4 is 12 over 4 plus 1 is 5. That's my a2. If I plug in 3, 3 times 9 is 27. Over 9 plus 1 is 10. I plug in 4. 3 times 16 is 48. Over, sorry, no, that's right, yeah. Over 16 plus 1 is 17. And finally, plugging in 5, 3 times 25 is 75. Over 25 plus 1, which is 26. And you might notice on the, well, in fact, let's do one big one, right? If n equals 1,000, we get sure. 1,000 squared is 1,000,000. 3 times 1,000,000 is 3 million. Over 1,000,001. So I wouldn't be surprised at all if the limit here was 3, because it looks like that fraction is really, really close to 3. Now, there's a long way of doing this, which we did previously, where you say, okay, we take the limit as n goes to infinity, and again, I'm going to divide everything by the highest power of n in the denominator, right? If the higher power is in the numerator, we're still going to use the one in the denominator, and we'll see another example of that in a minute. So you could say this is going to be the limit as n goes to infinity of 3n squared over n squared over n squared over n squared plus 1 over n squared. And then that's going to be the limit as n goes to infinity of 3 over 1 plus 1 over n squared. This goes to 0, so we get 3.
I had a question.
Sure, one sec. I want to say a thing before you ask. So what we're going to see specifically for sequences like this, where it's powers of n or whatever your variable is over powers of whatever your variable is, if the degrees are the same, the limit's always going to be the quotient of the leading coefficients, in this case 3 over 1. Go ahead, Emily.
That's what I was going to ask.
I thought it might be what you were going to ask. Okay, so yeah, so as long as the powers are the same, the limit's always going to be just that quotient. So for example, we could say, okay, here's a sequence. A sub n is, let's make it something kind of gross, like 5n cubed plus 2n minus 1 over 8n cubed minus 7n squared plus 16. And you could, if you wanted to, and maybe your teacher wants you to, divide everything by n cubed, right? And that would be the work. So if your teacher wants you to show the work, that's probably the work they want you to show for this. So, oh, sorry, it's not equal to the limit. Sorry, I'm just trying to find, sorry. This is not equal to its own limit. So limit as n goes to infinity of this expression, I'm going to divide everything by n cubed, and I'm going to do it fast. So 5n cubed divided by n cubed is 5. 2n divided by n cubed, one of the n's cancels, and I get 2 over n squared. Minus 1 over n cubed is minus 1 over n cubed. the bottom, 8n cubed over n cubed is 8, minus 7n cubed over, sorry, minus 7n squared over n cubed is going to be minus 7 over n because 2 of the n's will cancel, and then 16 over n cubed. And then any of these things that are divided by n to a positive power, they're all going to go to 0. I don't think you have to show this work all the time, but if your teacher wants you to show the work, this is one way of showing the work. Go ahead.
So, like what you've been doing for like the other examples, like, why do you divide it by like n, or like n squared and n cubed?
So the reason for doing that is because it makes it so that we can see what happens. So let me ask you, if we didn't divide by n or n squared or n cubed, if I just look at this, if I just try plugging in bigger and bigger numbers, I get what's called an indeterminate form, right? If I let n go to infinity, I'm essentially going to get 3 times infinity squared over infinity squared plus 1. And I don't know, so I mean, the top is definitely infinitely large. The bottom is also infinitely large. And infinity divided by infinity is not known what it is without doing more work. I don't know if this infinity is bigger than that infinity, or if this one's bigger, or if they're about the same, or if one of them is exactly 3 times larger than the other one. So this process of dividing by the highest power of n in the denominator allows us to simplify this in a way that we can actually tell what the limit's supposed to be.
Oh, okay.
So let's look at another example. In fact, yeah. So I'll remind you, because it does come up pretty often, if the powers on the top, I really should say, if the degree on the top and the bottom, meaning the highest power on the top and the bottom, are the same, the limit is just the quotient of those leading coefficients. If they're different, we have other things happening. So let's say our sequence is b sub n equal to, I don't know, 2n over 3n squared plus 1. And we could write it out in terms, but I mean, it's a good deal to write out the terms, right? b1 is definitely 2 over 3 plus 1. b2 is 4 over 3 times 12. 4 is 12 plus 1 is 13. b3 is going to be 6 over 3 times 9, so we're right, 28. b4 is going to be 8 over 49, etc. Right? And sometimes this is helpful. Sometimes this really isn't that helpful, but sometimes we're asked to do it, so we need to be able to plug in the numbers. But then what I really want to know is, what, if anything, does this sequence converge to? So the limit as n goes to infinity of b sub n, which is the limit as n goes to infinity, 2n over 3n squared plus 1. Now we'll mention here as well, if we plug in infinity, we get infinity on the top, we get infinity on the bottom. I don't know what that is. I have to do some work. So here, just like the previous ones, we're going to divide the top and bottom by the highest power of n in the denominator, which still is the highest power. If I do that, the limit as n goes to infinity of 2n over n squared over 3n squared over n squared plus 1 over n squared. Some people prefer to factor out an n squared. It's the same thing, really, but you can do whatever you like. So then I get the limit as n goes to infinity of, on top I have 1 over n. On the bottom I have 3 plus 1 over n squared. Where does the 1 over n go? Or I should say, what's the limit as n goes to infinity of 1 over n?
0?
Yeah. And then on the bottom, I get 3 plus 0 again. So here I get 0 over 3, which is 0. And what is true for these, for these rational type functions where the degree on top is less than the degree on the bottom is that the limit always ends up being 0. One of my students a long time ago said, why don't you just write it so that they have the same degree? Meaning, why don't you write it so it's the limit as n goes to infinity of 0n squared plus 2n over 3n squared plus 1. I was like, oh, that's really clever. That totally works. So if you want to do that for ones where the degree on top is less, you totally can. And then you can just say, oh, well, the highest powers are n squared. They're the same. So the limit is the quotient of the leading coefficients, which is 0 over 3, which is 0. Kind of feels like cheating, but it totally works.
I had a question about the process really quick. When you had the 2n over n squared, how did you get the 1n from that? In the numerator, the 2n over.
Oh, sorry, I lost the 2. I apologize.
Oh, no, it's okay.
That should have been a 2 over n. Yeah.
Okay. I was just making sure.
No, definitely. If you see an error, definitely make sure you ask me about it, because it's very easy to make a mistake. And I don't want you guys to think that I'm doing something that's right when it's really not.
Yeah. Well, so that would still be 0 though, right?
It would still be 0. Yeah, exactly. Okay. So in the same sort of way, without really making any effort, I could say that the sequence a sub n equal to 5n to the 4th plus 7n plus 1 over 2n to the 6th plus 5n squared plus 3n plus 2. I know without doing any work at all, this converges to 0. Meaning the limit as n goes to infinity of an is the limit as n goes to infinity of this whole thing here, 5n to the 4th plus 7n plus 1 over 2n to the 6th plus 5n squared plus 3n plus 2. That has to be 0, because the degree on top is less than the degree on the bottom, or the highest power on top is less than the highest power on the bottom. You should still show the work. I'm not going to show the work for this one, but the work here would be to divide everything by n to the 6th. So then after you take the limit, all the things on top are going to go to 0. So I'm going to divide by n to the 6th. This will be 5 over n squared. This will be 7 over n to the 5th. This will be 1 over n to the 6th. And all of those will go to 0 as n goes to infinity. On the bottom, this first term, I'm going to divide that by n to the 6th. You'll just get 2. And then everything else will be things that will be divided by a power of n, which will go to 0. So everything goes to 0 except for this is 2, so you get 0 over 2, which is 0. So really we would get, 0 plus 0 plus 0 over 2 plus 0 plus 0 plus 0. But again, I think it's really fine if you say, oh yeah, I know when the degree on top is less, the limit's going to be 0.
I have a question.
So that begs the question, what about something where the degree on top is larger? Again, it's still an infinity over infinity type of limit. And I should emphasize, when we say infinity over infinity, we're talking about what's called an indeterminate form. Just like a 0 over 0 limit is an indeterminate form, so is an infinity over infinity. And what that means when someone says it's an indeterminate form is that it can end up being anything, right? In this one, infinity over infinity was 0. In this one, infinity over infinity was also 0. But in some of the previous ones, infinity over infinity was a different number, like 3 or 2 or 5/8. So now here's where it's important to remember the whole thing about what we divide by. We're going to divide by n to the highest power that's in the denominator. So we're going to say, okay, if I want to find the limit as n goes to infinity of 2n squared over n plus 1, we're going to divide everything by n. So I'm going to get 2n squared over n over n plus 1 over n, which is going to be the limit as n goes to infinity of 2n over 1 plus 1 over n. And now look what happens. The denominator goes to 1 plus 0, right? This goes to 0. But the numerator is still going to infinity. So I'm going to get infinity over 1, which is infinity. So here you could either say the limit doesn't exist, but it's more accurate to say that the limit doesn't exist because it's getting infinitely large. So we say a limit is equal to infinity, although you can't really equal infinity. But what we mean is that the expression, as n gets larger, the expression is also getting larger and larger without bound.
So would that make that divergent then?
Yes, so this sequence is definitely divergent. Now here you could say specifically that it diverges to infinity. Sometimes things diverge in a way that you can say what they diverge to. Sometimes they just diverge and you can't say anything more than that. Like this next example.
I had a question.
Go ahead.
The reason why is it the reason that we divide by the highest number on the bottom? Is it because of like the first, or the one that if you have a denominator that has an n in it, it's equal to 0?
So the issue. So here's the real issue, Emily. If we instead divided by the highest power that was in the numerator, we would end up with. So if I did that, I would get 2 over n over n squared is 1 over n. 1 over n squared is 1 over n squared. I would get 2 over 0. And the problem with dividing by 0 is it's not always super clear if this is getting infinitely large or negatively infinitely large. Mm-hmm. That's the real issue at hand here. Let me show you another example. Say I have the limit. Sorry, I want the sequence first. Let's see, what do I want? Sure. Let's write it kind of out of order. So let's say we've got 6n minus n cubed over 2n squared plus 1. And as you can tell, I've kind of stopped writing out the first 5 terms. That's not something, not that that's something that is not important, but it's not really what this is all about. Like it definitely is something we do some of the time. Like we totally could here, right? A sub 1 would be 6 minus 1 over 2 plus 1, which is 5/3. A sub 2 would be 12 minus 8 over 2 times 4 is 8 plus 1, 4 over 9. A sub 3 would be 18 minus 27 over 2 times 9. So it is kind of useful to write out the first 2 terms because here we see that things actually start becoming negative. So that might give us a clue as to what's going to happen here. 24 minus 4 cubed is 64 over 2 times 16 plus 1. So we get negative 40 over 33. So, okay, we see what the first 4 terms are doing, but we don't really know what's going to happen. But I do know what I'm going to do, which is I'm going to divide everything by n squared. But let me actually show you, let's say we went the wrong way for a second. Let's say we divided by n cubed. So I want to find the limit as n goes to infinity of 6n minus n cubed over 2n squared plus 1. If we divide by n cubed, look what happens. So 6n over n cubed is 6 over n squared. I'm doing the simplifying without just writing all the division by n cubed. N cubed divided by n cubed is 1. 2n squared divided by n cubed is 2 over n. And 1 divided by n cubed is 1 over n cubed. Okay, so then I get 0 minus 1 over 0 plus 0, which is negative 1 over 0. But the problem is, I don't really know if this denominator is positive or negative. Mm-hmm. This one, you can probably tell it's actually positive, but if I change this to a minus 1, it would be way less clear if the denominator was small and close to 0 from the negative side or from the positive side. And so I want to avoid that confusion. And the way I avoid that confusion is instead of dividing by the highest power in the numerator, I divide by the highest power in the denominator.
Okay.
So I do that, I get the limit as n goes to infinity of 6n over n squared minus n cubed over n squared over 2n squared over n squared plus 1 over n squared. And that simplifies as the limit as n goes to infinity. 6n over n squared is 6 over n cubed over n squared is n, 2n squared over n squared is 2, 1 over n squared is 1 over n squared. And then the things divided by n, those go to 0. So I get 0 minus infinity over 2 plus 0, which is negative infinity. So we would say that this series, or sorry, this sequence diverges to negative infinity. Okay.
Thank you.
We also have alternating sequences. So sometimes you'll see a sequence and they'll throw in a -1 to a power in front of it. Like, for example, the sequence a sub n equal to -1 to the n plus 1 times 3n plus 2 over n plus 1. Let's write out the first 4 or 5 terms. So this is going to alternate, and it's going to start out, sometimes it's going to start out on a positive term, sometimes it's going to start on a negative term, depending on how this is written. So the first term is going to be -1 to the 1 plus 1 is -1 squared, which is positive 1, so it's going to be a positive, and then plug in 1 here, 3 plus 2 is 5 over 2. And then a sub 2 is -1 to the 2 plus 1 to -1 cubed, which is negative, so that's going to change the sign. So it's going to go positive, negative, positive, negative, positive, negative forever and ever. And I'm going to plug in 2 here and get 6 plus 2 is 8 over 3. And then I should point out, instead of plugging in each time, you can kind of, for this one specifically, you kind of see what's going to happen. Every time you plug in the next value of n, the top is going to get 3 larger and the bottom is going to get 1 larger. So I could just say, oh, instead of actually plugging in 3 and getting 9 plus 2 is 11 over 3 plus 1 is 4, I could say, well, the top's going to get 3 bigger, the bottom's going to get 1 bigger. And then the next thing that's going to happen for the next one. For the next one, the top's going to get 3 bigger, the bottom's going to get 1 bigger. But it's going to be negative because of the alternatingness. And then for the next one, the top's going to get 3 bigger, the bottom's going to get 1 bigger. That only really works for ones where you have like just n to the first power on the top and the bottom, right? If it's higher powers, you can't really say that. But it does, the reason I point this out is because someone might give you these first 5 terms and then ask you to find what the sequence was in the first place. And if you can see that the numerators are just increasing by the same amount each time, and the denominators are just increasing by the same amount each time, that you've got something where it's linear on top and linear on the bottom, and you just have to figure out what the kind of thing looks like. So what's the limit of this? Well, that's a good question. So I'm going to ignore this part for just a second. So we know, so look at instead the non-alternating part, the non-oscillating part. And everybody, I think at this point, everyone should be able to tell me that this limit of this sequence with 3n plus 2 over n plus 1 should equal what number?
3.
Yeah, exactly. So that means, again, what that means, it doesn't mean it ever necessarily equals 3, although sometimes it does. It just means it's getting closer and closer to 3. So when n is 1,000, right? Right. So when n is 1,000, we get 3,002 over 1,001. It's actually when n is 1,000, we actually get negative that. When n is 1,001, we get 3,005 over 1,002. The problem is this number is really, really close to -3, and this number is really, really close to +3. So if you have an alternating sequence, and the non-alternating part is getting close to a positive number, that means you're alternating back and forth between being close to 3 and then -3, 3 and then -3, and then 3. So the problem is the limit doesn't exist. Because if you're going back and forth between being closer and closer to two different numbers, we're not getting close to one specific number. And that is what the meaning of what a limit existing is that the expression is getting closer and closer to one specific number. So this limit as n goes to infinity of the sequence -1 to the n plus 1 times 3n plus 2 over n plus 1, this limit does not exist because we keep oscillating back and forth between +3 or numbers closer to +3 and closer to -3. Here's a fun fact. Fun might be overselling. Here's a fact. We would also, so I would also say, right, that this sequence does diverge, right? If it's not convergent, it is divergent. Those are the only two options, right? So if it doesn't converge to a single number, we say it diverges. What if my sequence was -1 to the n times 5n squared over 2n cubed plus 1? Well, we know it's going to alternate, right? My first term is going to be negative, right? Because -1 to the 1, 5 over 2 plus 1. My second term is going to be positive. 5 times 2 squared is 20, over 2 times 2 cubed is 8, times 2 is 16, plus 1 is 17. And then the third term, right, they're going to get big, right? The third term is going to be negative. 5 times 9 is 45, over 2 times 27 plus 1 is 55, and so on. So the question here is, does this limit exist? Well, it's still alternating back and forth. But here, if I look at the limit as n goes to infinity of just the non-alternating sequence, 5n squared over 2n cubed plus 1. Everybody, what's the limit of this sequence where the degree on top is smaller?
0.
Right. And so here's the thing. My terms are getting closer and closer to 0. So it doesn't matter if I'm positive or negative. Right? So here's kind of what's happening. And I kind of like to do this graphically. Right, so I start at 1, -5/3. And then I plug in 2 and I'm at positive 27. 17 is a little bit bigger than 1. And then when I plug in 3, I have a -45/2, which is actually small, like closer to 0 than -1. So kind of like here. And then my next number is going to be closer to 0. My next number is going to be closer to 0 but negative. The next one's closer to 0 but positive. Right, so I keep getting closer and closer to 0 on either side. So the limit is 0 because even though I'm alternating above and below, I'm still getting, sorry, I'm trying to like show you guys, I'm still like alternating above and below, but getting closer and closer to them both being 0. So there's actually a theorem that says an alternating sequence converges if and only if it converges to 0. So if you have an alternating sequence, the only thing it might converge to is 0. Otherwise, it's going to diverge. So we can say that the limit as n goes to infinity of this alternating sequence, -1 to the n times 5n squared over 2n cubed plus 1 is 0. Let me show you one more that's in kind of a similar vein, but not quite the same.
Does it always does it always converge to 0 when the -1 is only to the nth power, not the n plus 1?
No, so this could have been n plus 1 as well.
Oh, okay.
It doesn't matter. So this just, whether it's n or n plus 1, basically just tells you if you start with the negative or start with the positive. So if it was n plus 1, we would have had positive, negative, positive, negative. But we still would have had terms that were either on the positive or the negative side getting closer to 0.
So it just depends on the 5n squared, that equation.
Because this thing is going to 0, that the alternating thing is also going to 0. Whereas over here, since the thing that, right, since this part, the non-alternating part was converging to not 0, it was converging to 3, then the alternating part is going back and forth between 3 and -3, which are far apart. Whereas 0 and -0 are the same. They're the same number, really.
Okay, thank you.
You're welcome.
And what does it converge to 0 again?
Say that one more time.
What does it converge to 0 again? The problem in the back.
So I guess you could say it this way. Fine, let me write. So you could actually write this. So I want to find the limit. Then goes to infinity of -1 to the n plus 1 times the thing, right? Which was 5 squared. And so this is just -1 or 1, right?
Mm-hmm.
So I can write this as the limit as n goes to infinity of -1 to the n plus 1 times the limit as n goes to infinity of 5. Oops, I wrote that backwards. Sorry. Sorry, that should be 5n squared over 2n cubed. But we know this is 0, right?
Yeah.
So I got the limit as n goes to infinity of -1 to the n plus 1 times 0. Okay. What's -1 to the n plus 1 times 0?
0. Okay.
So it's the limit of 0, which is 0. So that's the thing, right? This part's going to 0, and this part's either just 1 or -1. And whether it's 1 or -1, when you multiply it by 0, it's still 0.
Oh, okay.
Yeah, this is an excellent question.
Thank you.
Thank you. I'll just point out for this alternating sequence, -1 to the n plus 1 times 2n squared plus 3 over n plus 1. We know this part, since the degree on top is higher, is going to diverge to infinity. So we know that this limit here, as n goes to infinity of -1 to the n plus 1 over 2n squared plus 3 over n plus 1. Well, it's not actually going to infinity because it's oscillating back and forth or alternating back and forth. It's kind of either going to positive infinity or negative infinity, right? It's kind of bouncing. So instead of bouncing back and forth like the previous ones, where like it was bouncing back and forth, getting closer and closer to 0, this one's kind of doing the opposite thing, where so if you plug in 1, you're getting 5/2. Right, so I get like 5/2. And then when I plug in 2, I'm getting something bigger. Right, I'm getting 2 times 4, which is 8 plus 3 is 11 over 3. And then when I plug in 3, I get something even bigger. And then 4 is something even bigger. So what's happening here is we're diverging in both directions. And so what we're going to say is that this sequence is just divergent. We can't say it's divergent to infinity or to negative infinity because it's not specifically divergent to either one. And we would say that the limit does not exist. Not that it's infinity or negative infinity, just that it does not exist. Okay. Sure.
So whenever it doesn't dedicate like to a specific number, it's always gonna be, or it's always gonna be doesn't exist.
Yeah. So if the limit isn't getting close to one specific number, or either infinity or negative infinity, yeah, the limit's going to not exist, which is equivalent to saying the sequence is divergent.
Mm-hmm.
If the limit doesn't exist, or the limit is infinity or negative infinity, the sequence is divergent. If the limit exists and is a real number, not infinity or negative infinity, then we say that the sequence is convergent.
Okay.
Yeah. Couple more examples, and then we'll start talking about, yeah, sure. So if my sequence was, say, sure, why not? 9 times 2/3 to the nth power. Again, let's write out some terms here. So a sub 1 is 9 times 2/3, which is 6. A sub 2 is 9 times 2/3 squared, which is 9 times 4 ninths, which is 4. A sub 3 is going to be 9 times 2/3 cubed. I could say that 2/3 cubed is 8/27, so you multiply by 9, you get 8/3. But what's happening each time is I'm just multiplying by another 2/3. So I can say, well, right, the first term was 6. 6 times 2/3 is 4. 4 times 2/3 is 8/3. And the next term, which would be 9 times 2/3 to the 4th power, is going to be 8/3 times 2/3, which is 16 ninths. And then the next term would be 16 ninths times another 2/3, which is 32/27. And so on, and so on, and so on. And it looks like, as far as I can tell, my numbers are getting smaller, right? 6 times 2/3 is smaller, times 2/3 is smaller, times 2/3 is smaller, times 2/3 is smaller. So if I'm going to take the limit as n goes to infinity of 9 times 2/3 to the n, if you keep multiplying by a number like 2/3, what's going to happen?
It's going to go to 0 eventually.
Yep, sure is. And that's true for any number to a power if that number is less than 1. So I could take, right, the limit of this being 0, I can say the limit as n goes to infinity of, 99 hundredths to the nth power is also 0. Because if you keep multiplying this number that's less than 1 by itself, it's always going to get smaller and smaller and smaller. It's also true for negative numbers if they're between 1 and -1. So if I took, say, like the limit as n goes to infinity of -3/4 to the n, that's also going to have a limit that's 0. Because -3/4 times -3/4 got smaller in absolute value, right? It's going to be 9/16. And times another 3/4 is -27/64. So even though you're alternating back and forth between positive and negative numbers, those numbers are getting smaller and smaller and smaller. So the limit is 0. Yeah, let's see. Sure. Something to be aware of, because it does come up on occasion. Something like cosine of n pi. So here's the thing about cosine of n pi. The first term is cosine of pi, which is -1. The second term is cosine of 2 pi, which is +1. The third term is cosine of 3 pi, which is -1. The fourth term is cosine of 4 pi. Right? We're just going back and forth between 1 or -1, 1, -1, 1. So it is actually technically correct to also write this as -1 to the n. This and this are the same for every integer value of n. It's definitely not true if n is some fractional or irrational number. But then this sequence, -1, 1, -1, 1, -1, 1, -1, 1, -1, 1, it doesn't converge. It just goes back and forth between -1, 1, -1, 1, -1, 1. This definitely diverges. Right? We're not getting close to one specific number. All right, let's look at some recursive sequences. Maybe we'll even talk about my favorite recursive sequence. It's not, it's a pretty popular one, but yeah. We'll see. We'll see if we need to talk about it. So let's look at this recursive sequence. A sub n plus 1 equals to 1/2 times a sub n plus 5. And we're given that the first term, a sub 1, is equal to 4. So when you're dealing with recursive sequences, most of the time you pretty much have to be given a starting point. There might be examples where you don't have to be. I don't think that's typically the case. So I want to see I want to find the first 5 terms. So a sub 2. So again, when I'm finding a sub 2, I'm really finding a sub 1 plus 1. And a sub 1 plus 1 is equal to 1/2 times a sub 1 plus 5. Right, so I'm using the previous term to get the next term. That is the literal definition of being a recursive sequence. And then that's going to be 1/2 times 4 plus 5, which is 9 times, or 4.5, whatever you like. Okay, and then we're going to use that to find the next term. So the third term of the sequence is going to be, right, I'm setting n equal to, so here, right, here n equals 1, so I'm finding a sub 1 plus 1. Here n equals 2. I'm finding a sub 2 plus 1, which is 1/2 of a sub 2 plus 5, which is 1/2 of 9/2 plus 5. And then we do the math. 9/2 plus 5/2, sorry, 9/2 plus 5 is 9/2 plus 10/2, which is 19/2. So you get 1/2 times 19 over 2, which is 19 divided by 4. Or 4.75, if you like. Okay, keep going. So we're going to be a little bit less, right? The fourth term, I'm just going to use that in this formula. So it's going to be 1/2 of a sub 3 plus 5, which is going to be 1/2 of 4.75 plus 5. 1/2 of 4.75 plus 5 is going to be 875? That seems right. Yeah. And you can keep going, right? A sub 5 would be 1/2 of a sub 4 plus 5, which is 1/2 of 4.875 and 5. And that ends up being, I don't know, calculator. I really don't feel like I should be able to do that. I should. 0.065, it should be like 4.9375, I think. Let me check. Yeah, got it right. Feel good about that. Okay, so it looks like, so if you had to guess, what's the limit as n goes to infinity of a sub n? What does it look like our numbers are getting closer and closer and closer to?
5.
I would guess 5 too, right? It might not be 5. It might be something smaller than 5 or maybe something bigger than 5, but it's looking like 5. Okay. So the question is, for a recursive sequence, how do we figure out what the limit might be? So here's how we do it. So a recursive sequence converges when the next term is equal to the previous term, right? When a sub n plus 1 equals a sub n. Just one second, I can hear my, I'll be right back, right now. Sorry, one second, I think my cat might be locked. No, I just thought I heard a cat yelling, so I was making sure it wasn't like crap in the room. I thought I heard a cat yelling. I don't know, we're good. Okay, out cat. Sorry, I accidentally trapped my cat in the room the other day for a couple hours and I felt really bad about it. So I thought I heard the cat yelping. I wanted to make sure it was not trapped in the room. So not trapped in the room, but I just had to make sure. Anyway, sorry. So recursive sequences converge when the next term is equal to the previous term, right? Because if you plug in a number, you get back the number. So we can actually see with that kind of idea that 5 is a possible limit here, right? If I take my sequence and if I plug in 5, what happens? Well, if an is 5, then a sub n plus 1 is 1/2 of 5 plus 5, which is 5. And then I would plug that back in, and then we get it back again. So once you get to this thing, which is called a fixed point, that basically means when you plug it in, you get the same thing back. And that's definitely a candidate for a limit, right? Because we're getting closer and closer to this number where if you plug it in, you get it back. So that's actually how we discover what the limit is. Or I shouldn't say limit, because you can find more than one candidate for a limit, and they're not always all going to be limits. But we can find the fixed points of the sequence by making this assumption that a sub n plus 1 is equal to a sub n. And we usually call it capital L for limits. So we're going to let a sub n plus 1 equal to a sub n equal to L. And we're going to plug that in for a sub n plus 1 and a sub n. So I'm going to plug in L equal to 1/2 of L plus 5. And then we're going to solve for L. Multiply both sides by 2. Subtract L. There you go. So L equal to 5 is a fixed point. Of the recursive sequence. Okay, I definitely hear my cat going. Sorry, listen. I don't know what's going on. I think she's just being crazy. Okay, so I should mention here, a fixed point is not necessarily the limit. A fixed point is a candidate for the limit, but it might not always be the limit. Here, it totally is. But there could be other, if we'd started somewhere different, we might have ended up with not that value. Although I think this one, no matter where you start, you do end up getting closer and closer to 5. So let's look at some more examples. For example, let's look at the following. Let's look at, what have I got here? A sub n plus 1 equal to the square root of 2 times a sub n. And we're starting with a sub 1 equal to 3. All right, so we can either find some values. The values are kind of less nice to find. So a sub 2 is the square root of 2 times 3, which is the square root of 6, which is approximately 2.45. And then a sub 3 would be the square root of 2 times the square root of 6, which just starts getting uglier, right? It's going to be approximately 2.21. And then a sub 4 is the square root of 2 times this, which is the square root of 2 times the square root, right? It's going to get real nasty. And that's approximately, what do we got here? 2.10. And then the next one would be the square root of 2 times all of that, which would be the square root of 2 times the square root of 2 square root of 6, which is gross, which is approximately 2.05. So it's looking like the limit of the sequence is probably 2. It might not be exactly 2. We don't actually know that. But here's what we know. We know that we can find the fixed points, and we can then make a pretty educated guess. So again, to find the fixed points, we just set all the a sub whatever is equal to L. So replace a sub n plus 1 and a sub n with L. So I've got L equal to the square root of 2L. And then I want to solve for L. I can already, so let me ask you guys, without even doing any work, is 2 a solution here? If you plug in 2 for L, are these sides equal? Yeah.
Yeah.
Equals the square root of 2 times 2. So 2 would be a solution. 0 would also be a solution. 0 equals the square root of 2 times 0. In fact, those are going to be the solutions we find. Now, we're still going to do the work of solving it. We're going to square both sides. We're going to subtract 2L. We're going to factor on L. And then we're going to get L equal to 0 and L equal to 2. Now, we know that 0 is definitely not the limit of the sequence, right? The number, well, I mean, I guess it could be, but we're pretty sure it's not, right? It looks way more like 2 is the limit here. But again, I should point out, there isn't a, we don't have a great method yet of looking at the fixed points and knowing without kind of doing some just analysis of plugging some numbers in what the limit's actually going to be. It's interesting to ask the question, right? If we started somewhere else, like at somewhere not 3, would we still get this same limit being 2, or would it end up being 0? And that's a really good question. Like, so if I started at 1 and I plugged in 1, then my next term would be the square root of 2, and then, which is 1.4-ish. And then the next one would be the square root of 2 times the square root of 2, which is getting bigger. So yeah, it kind of looks like if we started at 1, we would grow larger and larger towards 2. I think the only way you could get 0 as your limit is if you started at 0. If you plug in 0, you get 0 back. And if you plug in 0, you get 0 back, right? So if you ever start at a fixed point, you're just done. Yeah. I have this one example that's kind of crazy. It's that one. Okay, good. We'll get there in a second. Let's look at a couple more examples. Let's look at a sub n plus 1 equal to 12 over 1 plus a sub n. What time is it? Okay, it's 10 o'clock. Another couple. Sorry, I just want to make sure I'm addressing the things people ask me about. Jack, we can definitely look at some of those questions from 2.2. Yeah, cool. All right. So let's look at a couple more recursive ones, and then we'll look at some of those problems from section 2.2, or at least similar problems. Sorry, so this is my sequence. And let's find the, oh, I'm sorry, I'm starting at 1. And let's go ahead and find the fixed points before we even do anything else. In fact, why don't you guys find the fixed points? So set both of these equal to L and solve for L. I'll be right back. So apparently my cat is having one of those days. I think it's because I didn't do the litter yet, so I went and did the litter, but she's just yelling and yelling and yelling. Like the spoiled cat that she is. Okay, anyway. Sorry, enough about my cat. So solving this, I get L times 1 plus L equal to 12. I multiply this out. I get L squared plus L minus 12 equal to 0. I factor. And then I get L equal to -4 or L equal to 3. And so here's what I'll observe. If I'm going to start at 1, I'm going to end up getting positive results, right? If I plug in 1, I'm going to get 12 over something positive, which will be positive. And if I plug in the next number, I'm going to right, I'm always going to get 12 over something positive, which is going to give me back something positive. So if I'm starting at a positive number, I'm already sure that this can't be the limit, right? It's just not possible. So, but then I should look and see, I'm actually getting close to 3. So I plug in 1, I get a sub 2 is 12 over 1 plus 1, which is 6. And then a sub 3 is 12 over 1 plus 6, which is 12 sevenths. And then a sub 4 is 12 over 1 plus 12 sevenths, which is not very nice. It's about 4.42. And then a sub 5 is 12 over 1 plus 4.42, which is about, what have I got here? 2.21. And if you keep going, the numbers you get, the next one is 3.73, the next is 2.53, the next is 3.39. It looks like we're bouncing back and forth above and below 3. And so this one does get closer and closer to 3. It just takes a little while to see it. Yeah, so typically, one of your fixed points is usually the limit. That's not always true, like in this next example. So let's say we have a sub n plus 1 equal to 4 over a sub n. And we start at a sub n equal to 1. So check this out. A sub 2 is going to be 4 over 1, which is 4. A sub 3 is going to be 4 over 4, which is 1. A sub 4 is going to be 4 over 1, which is 4. I think you can see what's happening here. 4, 1, 4, 1, 4, 1, 4, right? We're just going to keep back and forth between 1 and 4. So at least if we start at 1 here, the limit doesn't, right? There isn't going to be a limit. The sequence is oscillating back and forth between 1 and 4. So you can definitely say that this is divergent, right? It does not converge. And we can see as well that the fixed points, so if we set both of those equal to L, and multiply both sides by L squared equals 4, L equals plus or minus 2, which is definitely not what we plugged in, right? If you did start at 2, then you would be, that would be your limit, right? Because you plug in 2 and 4 over 2 would be 2, and then 4 over 2 would be 2, and then, right, you just keep doing it. But I think actually, any number that isn't 2 or -2 is going to make it diverge, right? What if we started at 3, right? We'll split the difference, not 1, not 2, but 3. If I start at 3, then a sub 2 is going to be 4 divided by 3, which is 4/3. And then a sub 3 is going to be 4 divided by 4/3, which is 4 times 3/4. I don't know, I'm back in the same sort of problem, right? I started at 3, I got 4/3, I'm back at 3. The next one's going to be 4/3, the next one's going to be 3. So this is an example of a sequence that really doesn't converge unless you actually start at the fixed point. Otherwise, it's just going to bounce back and forth between two different numbers. It's kind of bizarre, but it definitely is true. Okay.
I had a question.
Go ahead.
Is that only when a sub n is on the denominator by itself?
I mean, I wouldn't make such a specific categorization. Like it might be, but it might just be that. Like, I mean, I think if you yeah, if you did any sequence that was a sub n plus 1 equals some positive number over a sub n, you're going to get the same sort of result, where the fixed points are the square root of that positive number, right? Just like it was here, the fixed point was the square root of 4 and the negative square root of 4. And then it's just going to keep bouncing back and forth between whatever you started at and whatever its reciprocal is, right? So like if I start, for example, if I start at a sub n equal to 2, then the next, a sub 1 equal to 2, then the next one's going to be that number over 2. And then the next one's going to be that number over 2. But that's just going to be that number times 2 over that number. The numbers cancel and you're back where you started. So anything that's like this, you definitely have this kind of relationship where you just bounce back and forth between two different numbers.
Okay, thank you.
But I will say, there are certainly other sequences that also diverge in this kind of way, where you're kind of stuck between two numbers, neither one of them getting closer to the actual limit of the sequence. Or I should say, to the potential limit. Because I should say, right, I should back up for a second. This sequence doesn't have a limit, right? It's got fixed points that are candidates to be the limit, but neither of them actually is the limit. The limit does not exist here. The sequence is divergent. So yeah, it took me a while when I was first teaching this class to really kind of make sure that I understood the language there that I was saying. There's a difference between a fixed point and a limit. A limit is a fixed point, but a fixed point is just a candidate for a limit. Kind of like how all, what's that? I was gonna say something dumb, right? All spiders are bugs, but not all bugs are spiders, right? Kind of like that, something like that. All right, let me see. We got about 10 minutes. I did want to. So, Jack, you had asked about questions 18, 21, and 28. Yeah. I think we did one like 21, so I'm not going to address that, but I'll definitely address 18 and 28. So let's look at something like 18. I'm going to pick specific numbers though. The limit is x goes to infinity. So again, limits where x goes to infinity or n goes to infinity, it's the same kind of deal. Right? It's just that now when you're in section 2.2, you're not just using integer values of your x thing, right? X can be any real number that's getting larger and larger and larger. It doesn't really make a difference, but it is a small difference. And we've got, yeah. So let's say we've got the square root of x squared plus 8x minus the square root of x squared plus, sure. Let's make it fun. Okay. So here we have another different type of indeterminate form. This square root is getting infinitely large. This square root is also getting infinitely large. And infinity minus infinity could be anything. It could be 0. It could be infinity. It could be negative infinity. It could be 5, right? There are lots of different options. It could literally be anything. So that's why we have to do more work. And the work for dealing with a square root minus a square root, where it's an infinity minus infinity, is to make it into a fraction. So the limit is x goes to infinity. Of the square root of x squared plus 8x minus the square root of x squared plus 3x all over 1 times the conjugate. The square root of x squared plus 8x minus the square, plus the square root of x squared plus 3x over the same thing. Okay. So the whole point of multiplying by the conjugate is that it makes the part you're multiplying, it's the conjugate of, right? The top part here is going to be nice. We're going to get this times this, which is just x squared plus 8x. The middle terms cancel, right? That's the reason you multiply by the conjugate. You get this square root of x squared plus 8x times the square root of x squared plus 3x, and then you get minus the square root of x squared plus 3x times the square root of x squared plus 8x. And those exactly cancel out. And then you get minus the square root of x squared plus 3x times the square root of x squared plus 3x, which is x squared plus 3x. And it is super important that you distribute, right, that it's minus all of that. And the bottom is just this. Okay, simplifying the top is just going to be 5x. Right, the x squareds cancel, 8x minus 3x is 5x. Okay. Bottom's still the same. So here's what we have to do for the bottom. And this is where things are a little tricky. I kind of want this to end up being like one of our rational functions, like the limit as n goes to infinity of 2n squared over n squared plus 1, where the degree on top and the degree on the bottom are the same. And although the bottom isn't a rational function, right, it's not a polynomial because they're square roots, it still kind of acts like one, and it still kind of has a degree. And the degree on the bottom is actually kind of like 1, because essentially the highest power on the bottom is the square root of x squared. And the highest power here is the square root of x squared. So what we're actually going to do, and this is where it's a little tricky, is we're going to factor out an x squared from the square root. So I'm going to write this as the square root of x squared times 1 plus 8 over x. And I'm going to write this as the square root of x squared times 1 plus 3 over x. Right, if I multiply that back in, x squared times 1 is x squared, and x squared times 8 over x is 8 times x. Same deal there. All right, so now here is a question that is kind of tricky, but not that tricky. What's the square root of x squared?
X.
It is, well, for sure here it is x. More generally though, it's actually the absolute value of x. But here, since x is going to infinity, that means x is already positive, and the absolute value of x is just x, because the absolute value of a positive number is just that positive number. So here's what we can say. This is equal to the limit as x goes to infinity of 5x over x, right, the square root of x squared, times the square root of 1 plus 8 over x, plus x times the square root of 1 plus 3 over x. Okay, here's what I'm going to do. Since I'm almost out of room on this board, I'm going to kind of cheat a little bit. So from these two terms, I'm going to factor out an x. So I'm going to rewrite the denominator as x times all that. And then I can cancel the x on the top with the x I just factored out. And so look, I'm left with 5 over, this part goes to 0, and this part goes to 0. So I've got the square root of 1 plus the square root of 1, which is 5 over 2. So the limit of this is 5 halves. Kind of nuts. These square root minus another square root ones are kind of a pain. Here's the good news. The other question, number 28 on this section, is way easier to deal with.
How did you get the square root of 1 plus the square root of 1?
Sorry. So the way I got the square root of 1 plus the square root of 1 is, so in this term here, which is the square root of 1 plus 8 over x, as x goes to infinity, 8 divided by x gets smaller and smaller and smaller. It goes to 0. So here I've got 1 plus 0, which is the square, it's in the square root, and I get the same thing here. This 3 over x goes to 0, so I got the square root of 1 plus 0. Does that answer your question?
Yeah.
Cool. Okay.
Excuse me.
Other questions?
Yeah. So if x approach to negative infinity instead, will the absolute bar change?
Yeah, so there's two things there which I want to address. And I was going to say that, but it actually, so if we were starting here and x was going to negative infinity, we would have that the square root of x squared would be the absolute value of x, which would be negative x. So if we were doing this limit from here and it was x approaching negative infinity, our answer would actually end up being negative 5/2 because we'd have an extra factor of a negative in the denominator. I should also point out though, if you actually started this question up here with x going to negative infinity, no, actually it would be okay. That'd be fine. Yeah. So sometimes there's a weirdness where it doesn't work out, but this is actually fine. So yeah, if x was going to minus infinity, our answer would end up being minus 5/2 because we would have a minus x that was the square root of x squared. So the square root of x squared is equal to x if x is positive, but it's equal to negative x if x is negative. And if you're going to negative infinity, your x is definitely negative.
Okay, thank you very much.
You're welcome. I know we're out of time, but this last question we can do very, very quickly. And I do want to show it to you guys because I think it's worthwhile. So it'll just take like a minute, maybe less, maybe more. So I'm going to change it up just slightly. So let's say it's the limit as x goes to negative infinity of the natural log of, what do I want here? Sure. 2x cubed minus the natural log of x cubed plus 5. And the whole idea here is that we're going to use the rules of logarithms. The natural log of something minus the natural log of something else is the natural log of this thing divided by that thing. So it's the natural log of 2x cubed over x cubed plus 5. And then, if I'm taking the limit as x goes to infinity or negative infinity, I can still use the same rules about coefficients, right? So if I do, so in fact, what I can really do is I can bring in the limit inside. So I can really write this as the natural log of the limit as x goes to negative infinity of 2x cubed over x cubed plus 5. And we know what this limit is, right? We dealt with these like the whole first part of class today. What's the limit as x goes to negative infinity of 2x cubed over x cubed plus 5?
2.
Exactly. So our answer is the natural log of 2. That's it.
Thank you for going over that one.
You're very welcome. So in the one in the book, your answer is obviously going to be slightly different, but it's essentially the same thing.
Wait, why is it 2?
What's that?
Why is it 2 again?
Well, so we can do what we were doing before and say, so we could say that this is the natural log of the limit as x goes to minus infinity, and we can divide everything in the top and bottom by x cubed. So 2x cubed over x cubed is 2, x cubed over x cubed is 1, and 5 over x cubed is 5 over x cubed. And then, as x gets really, really, really large, or really, really negatively large, 5 divided by a large number, whether it's positive or negative, still gets very, very small. So this 5 divided by x cubed goes to 0 as x gets really, really negatively big. And then you get 2 over 1 plus 0, which is 2. So that's how
okay.
log of 2.
Okay.
So I will stress, you guys will probably see a lot of things like this, where you have a rational function and the degree on top and the degree on the bottom is the same. So the limit, whether you're going to negative infinity or positive infinity, the limit is just the quotient of those leading coefficients. That comes up a lot.